Hi, my name is Ting-Lun, and I'm going to be talking about my research examining burst activity as a candidate biomarker of abnormal neurodynamics in pediatric dystonia. Now, dystonia is the third most common movement disorder in the US and is characterized by involuntary muscle contractions and abnormal posturing. And for children with severe dystonia, deep brain stimulation, or DBS, can reduce symptoms by delivering electrical stimulations to targeted deep brain regions through implanted electrodes. However, current DBS systems are largely open loop, meaning that they provide continuous stimulation without actually adapting to the patient's ongoing neural activity. This limits both precision and therapeutic efficiency. In the Sanger lab, in collaboration with the Children's Hospital of Orange County, we are investigating whether synchronous burst activity within the basal ganglia thalamocortical circuits in the brain can serve as a biomarker of dystonic symptom onset, with our broader goal being to use this physiological signal to support a closed-looped deep brain stimulation algorithm in which stimulation is delivered responsively rather based on real-time neural activity rather than continuously. In order to study this, I have developed a multi-stage burst detection pipeline for pediatric intracranial recordings, where at the single neuron level, burst events are identified using the rank surprise algorithm, which detects statistically significant sequences of temporally clustered activity. And these burst events are then integrated across multiple electrodes through a coactivity framework that characterizes synchronization at both a regional and network level, which allows us to move beyond isolated burst detection and instead assess how pathological activities emerges across the broader neural circuit. Building on all these burst findings, I have translated this framework into a real-time DBS algorithm and recently implemented it in a pediatric dystonic patient at the Children's Hospital, in which the system successfully delivered targeted stimulation through the implanted electrodes during this detected burst events with only 3 milliseconds of delay. And when we compare the stimulation delivered events with the stimulation withheld control events, we have observed a statistically significant reduction in both the mean and variance of post-stimulation neuroactivity, with these findings providing direct evidence that burst trigger stimulation can suppress abnormal neurodynamics. With future patient cases planned, we are continuing to refine both the detection framework and stimulation parameters to maximize the clinical effects and improve therapeutic performance. Thank you.